A reaction that can proceed in both the forward and reverse directions is called a reversible reaction. And a reversible reaction is indicated by a double-sided arrow. It can look like that, or it can look like that. But that indicates that a reaction takes place in both the forward and reverse directions, meaning that, of course, reactants will react and become products, but some products will then react and go back to being reactants. So this is an example of a reversible reaction here where we have water and carbon monoxide reacting to produce hydrogen and carbon dioxide. At the beginning, in this jar, we have equal numbers of moles of water and carbon dioxide, and it's important that that lid's on there. It has to be a closed container. If it wasn't a closed container, it would not come to equilibrium. So in jar B there, we can see the reaction begins to occur. We start to produce some products. We have a couple hydrogens, we have a couple carbon dioxides. As the reaction continues and time passes, more reactants are changed to products. But as that occurs, some of those products will start colliding with one another and they will go back to reactants. And so we then approach condition D. Although time continues to pass, the number of reactant and product molecules are the same. No further change is seen. And even though no further change is seen, that does not mean that the process stops. The process does continue, but it's just for every 1 mole of reactants that reacts to produce products, 1 mole of products reacts to produce reactants. So as the reaction proceeds, the forward reaction slows down. We talked about that the other day, where as the reaction proceeds, there are fewer reactants available, and so fewer collisions between reactants, and so the rate will slow. But as that forward rate slows, the reverse rate actually speeds up, because as I'm losing reactant, I'm forming product. So the concentrations of the product start to go up, they start reacting more, and so the rate of that reverse reaction goes up. And so the rate of the forward reaction slows, the rate of the reverse reaction increases until they are the same rate. That is when we are at equilibrium. Chemical equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. It is called dynamic equilibrium. That word dynamic is there to indicate that, like I said on the last slide, the process doesn't stop, it continues happening, but for every 1 mole of reactant that reacts, we have 1 mole of product that reacts. So equilibrium. So again, chemical equilibrium is not static, it is dynamic because the reactions are still occurring, but they are occurring at a constant rate. Because they are occurring at a constant rate, when we are at equilibrium, the concentrations of reactants and products no longer change. This is because the reactants and products are being depleted at the same rate at which they are being formed. So you can see here in this picture, at the beginning, at 0 seconds, we have 8 hydrogen, 8 iodine, and 0 HI. After 15 seconds, the reaction has begun, and now we've turned some of that reaction into product. We have 6 hydrogen, 6 iodine, and 4 HI. As the reaction continues, we have 4 hydrogen, 4 iodine, and 8 HI at 30 seconds, and then we see we have the same concentration at 45 seconds, meaning that this reaction has reached equilibrium. And even though hydrogen and iodine are combining to form HI is also decomposing to form hydrogen and iodine at the same rate. And so overall, the amount of each reactant and product is going to remain constant. There is something called the equilibrium constant, KEQ, that is a way to quantify the concentrations of reactants and products at equilibrium. So if we have this general chemical reaction where A and B are reactants, C and D are products, and then the lowercase letters are the coefficients, we can use the reactants and products and their coefficients to write what's called an equilibrium expression. Equilibrium expressions are always products, concentration, that's why they're in brackets, concentration of products raised to their coefficient over concentration of reactants raised to their coefficient. So if I was to write an equilibrium expression for this equation here, it would be KEQ equals concentration of products, so CH3OH, over concentration of reactants, so CO, times H2 And because H2 has a coefficient of 2, we're going to square that H2. Coefficients become exponents when you are writing equilibrium expressions. Also notice that when I have more than one reactant or product, you multiply. You do not add. So it's carbon monoxide times hydrogen, not plus. So for my second one, KEQ is going to be the concentration of HF squared, because it has that coefficient of 2, over the concentration of H2 times F2. And that's it. It's just that simple when it just says write the equilibrium expression. The value of K tells us a lot about the reaction. So if your KEQ is large, that means the forward reaction is favored. Another way that you can say that is you can say that the products, or I'll say that differently. You can say that it favors the products. Meaning at equilibrium, you will have a higher concentration of products than reactants. So in this reaction here, I have a KEQ of 1.9 times 10 to the 19th. That's very, 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 very large. So at equilibrium, I'm going to have mostly HBr, very little hydrogen and bromine. If KEQ is small, the reverse reaction is favored. Another way you can say that is that it favors the reactants, meaning that the concentration of reactants will be high and the concentration of products will be low. So my KEQ is 4.1 times 10 to the negative 31. That is very, 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 very small. At equilibrium, I will mostly have nitrogen and oxygen. I will have very few nitrogen monoxide molecules. So to summarize, if KEQ is very small, the reverse reaction is favored. The forward reaction does not proceed very far. If KEQ is very large, the forward reaction is favored. The forward reaction will proceed virtually to completion. If KEQ is about 1, neither direction is favored. We have about equal amounts of reactants and products at equilibrium. Not, exactly equal, but pretty close. So if I'm considering this general chemical reaction where A is turning into B, the reaction is allowed to come to equilibrium at 3 different temperatures, at which temperature is the equilibrium constant the largest. So again, when you have a large value of K, it tells you that the products are favored. So when I'm looking at T1, T2, and T3 here, I see that T3 has the most products. And so that would be an instance where, or that would be the temperature at which the value of K is large. At T2, value of K is definitely going to be more than 1, but T3 has more product than T2, and so that's why I picked that one. When you have heterogeneous equations, meaning that you have reactants and products that are in different states, you need to keep in mind when writing your equilibrium expressions that the concentrations of solids and liquids does not change. The concentration of a solid depends on the solid's density, which is going to be constant as long as some solid is present. Concentration of a pure liquid also will not change. So because of that, you do not include solids and liquids in an equilibrium expression. So if I was writing my KEQ expression for this, it would be CaO times CO2 over CaCO3. That's how we wrote it before. But the calcium oxide and the calcium carbonate are solids, so their concentration will not change. Effectively, their concentration is constant, so you can think of it as 1. So it's not going to affect the value of KEQ, and so we just write KEQ for this one is equal to the concentration of carbon dioxide. So if I'm doing this example here, I'm not going to include the 2 solids. KEQ is going to be CO2 concentration times H2O concentration, and that's going to be it, because it's products over reactants, but I don't have any reactants that I'm including in this equilibrium expression. For the next example, I have gaseous hydrogen, gaseous oxygen, and then liquid water. So I'm not going to write liquid water in my equilibrium expression, but the equilibrium expression still needs to be products over reactants. And so I'm going to put 1 as a placeholder. And so my equilibrium expression is going to be 1 is the concentration of H2 squared times the concentration of O2, or 1 over, the concentration of H2 squared times the concentration of O2. With, right here real quick, with heterogeneous equilibria, or with all equilibrium expressions, you you include gaseous things and you include aqueous things. So you do not include solid or liquid. You do include gas and aqueous. So if I have measured concentrations at equilibrium, I can use those to calculate the value of KEQ. So to do that, I would first write my equilibrium expression. So that's going to be HI squared over hydrogen times iodine. Then I would just plug in the values. So HI is 0.78 squared over 0.11 times 0.11. When you are, doing the math here, just be careful with your order of operations. Be careful with parentheses when you're typing things in on your calculator. Otherwise, you're going to get an incorrect answer. For this, I get about 50.28. K does not have a unit, so just 50.28. With correct sig figs, everything I was given had 2 sig figs, so we're going to do 50 point is how you do correct sig figs with that one. It's very important to understand that this equilibrium constant is just that. It is constant as long as temperature remains constant. When temperature changes, K changes. But if temperature is constant, K is going to be constant, regardless of initial concentrations of reactants or products. So this first one here, this is what I just did, where I started with 0.5 molar hydrogen and 0.5 molar iodine and 0 HI. I know that's the one I just did because those were the numbers I just used, my equilibrium concentrations that I just used. But notice, regardless of what I start with, in the second one, I start with no reactant. I start with 0.5 molar product. My equilibrium concentrations are much lower than they were in the previous reaction. But notice my ratio, my K value, is still 50, is still the same. So again, at constant temperature, it does not matter how much of each reactant or each product you start with. It doesn't actually even matter how much you end with, but the ratio of products to reactants will always be constant. So I have another example here where I'm going to write this equilibrium expression. They're all gaseous, so I'm going to include them all. So KEQ is hydrogen cubed times C2H2 over CH4 squared. I'm going to plug those numbers in. So 0.112 cubed times 0.0451 times 0.0203 squared. When I calculate this, I get a value of 0.154. And again, no unit for that, so just KEQ is 0.154. You can use KEQ to calculate an equilibrium concentration if you have the other equilibrium concentrations. So in this reaction, I'm given the KEQ, I'm given COF2 and CF4, and then I'm going to find carbon dioxide. So I'm going to write my equilibrium expression. CO2 times CF4 over COF2 squared. So then just plug in 2 is my unknown times 0.118 over 0.255 squared. Order of operations, do the algebra, solve, you're going to get a concentration of CO2 of 1.10 molar. And then just one more example. So I have KEQ is going to be concentration of HI squared over H2 times I2. So always start with writing your equilibrium expression. My KEQ here is 69. That's going to be my concentration of HI squared over 0.020 times 0.020. Again, do the algebra here, you're going to get concentration HI squared is going to be 0.0276. Square root both sides, and you'll get the concentration of HI is 0.17 molar.